Everyone, good morning and welcome to the lecture series session on EC402 nanoelectronics. My dear students, in the last class we have discussed about various methods of characterization and the characterization tools used for characterizing the nanostructures and nanomaterials. So in this module, we will be mainly discussing about two-dimensional systems, that is two-dimensional electronic systems and two-dimensional electronic behavior, and some of the devices which operates on two-dimensional electronic wave motion, especially the Mosfet, Mosfet and superlattices. So what is a two-dimensional electronic system? We have already discussed about what is one dimension, what is two dimension and what is three-dimensional systems. One of the most important recent developments in semiconductors has been the achievement of structures in which the electronic behavior is essentially two-dimensional. That is, at least for some phase of operation of the device, the carriers are confined in a potential well such that the electron motion in one direction is restricted. When the electron motion in one direction is restricted, what happens? That particular motion of the waveform, or that is, that particular motion of the electron wave can be quantized. So that quantization actually causes the plane wave motion of the electrons into a two-dimensional wave vector k, isn't it? So that we have already seen. Let's see, in bulky materials, of course, we have it's a three-dimensional system where the electron motion is actually, we have the electron motion as such, the plane wave motion. But in quantization, when we consider about the two-dimensional systems, the electron wave motions are actually quantized in one of the direction, at least one of the directions, at least one of the direction of the movement of the electron is restricted. So the electron movement is actually, that motion can be quantized. So such electron motions in one direction is restricted in the case of quantum well. So it can thus be quantized. So in that case, the electron wave motion will be a two-dimensional wave vector, isn't it? That we have seen. And that actually characterizes the motion in a plane normal to the confining potential. Such a confined system or confined motion of the electronic wave actually causes to have a confining potential, which is actually characterizing the motion of the electron in a plane normal, that is perpendicular to the confining potential. That is what is discussed here. The major system where such two-dimensional behavior has been studied are the metal oxide silicon structures, quantum wells and superlattices. Now we will see one by one what is the constructional features of most structures, what are the constructional features of quantum wells and some of the quantum wells, and what are all multiple quantum wells and some of its behaviors, and we will discuss about the superlattices and its characteristic features and some of the important phenomena which we come across the operation when we come across the operation of the superlattices. Okay. Now, two-dimensional behavior. What is meant by two-dimensional behavior? Two-dimensional behavior has been observed in heterojunctions of 3 to 5 compounds such as gallium arsenide, gallium aluminum arsenide layers compounds, or 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 or, or, or compounds such as gallium selenide, gallium selenide, and related 3 to 6 compounds. Actually, that are all coming under 3 to 5 compound table and 3 to 6 compound table. And graphite and intercalated graphite and electrons on the surface of liquid helium. Of course, two-dimensional behavior can be observed in all these materials. That we have seen some of the materials we have seen in the module 2, isn't it? Where the two-dimensional behavior has been observed. The gallium arsenide, gallium aluminum arsenide, or aluminum gallium arsenide, heterojunctions are important. So what is meant by heterojunctions then? Heterojunctions are actually junctions formed by two different materials of different lattice constants. Right? You know what is lattice constant? That also we will discuss in the later chapter, in the later portion of this, later section of this particular module. We have some of the strained structures, So same strained structures and its behavior, and that lattice constants and all those things you have to know. At least what is that particular what we call lattice constant for the material. So that we have to know. The gallium arsenide, gallium aluminum arsenide heterojunctions. So dissimilar materials of junctions having two different lattice constants. When it is joined together, it will form a heterojunction. Such heterojunctions are important for device applications because the lattice constants and the coefficient of expansion of the gallium arsenide and gallium aluminum arsenide are very similar. The coefficient of expansion of these two materials are almost constant, and lattice constants also, they are actually almost uh, very similar, right? This lattice matching permits the growth of high mobility thin film of gallium aluminum arsenide on a gallium arsenide substrate. So actually it is due to this particular facility that actually makes to grow a number of devices to be produced, and that are all considered to be high mobility electron devices. High mobility electron devices. We will see all those things in the subsequent sessions. Okay. The physical properties of the Mosfet lie in the two-dimensional behavior of the electrons in the channel inversion layer at low temperatures. We have seen in the electronic classes, we have already seen the constructional features of Mosfet. So the same concept of Mosfet feature can be used as a nano device if we confine the motion of electrons in a two dimensions. So it can be acted as a two-dimensional electron system or 2DEG system by confining it the motion of the electrons uh, in one direction. Okay, so it can be acted as a two-dimensional device, two-dimensional electron device. Okay, the physical properties of the MOSFET lie in the two-dimensional behavior of the electrons in the channel inversion layer at low temperatures. The two-dimensional behavior is associated with nearly plane wave electron states in the inversion layer. Actually, the two-dimensional behavior is associated with nearly plane wave electron states in the inversion layer. And what is the inversion layer also, all those things we will discuss. Okay. The potential Vz is associated with the electric field. Vz is equal to EEZ. We have already seen this equation. Vz for a two-dimensional system, the energy E is equal to Vz we have already seen. So Vz is equal to E into Ez because of the negative charge in the electron. A potential well is formed containing bound states described by quantized levels. That is the reason why uh, we can fabricate MOSFETs as a two-dimensional electron device. Okay, so this potential Vz which associated with the electric field Vz is equal to E into Ez. Ez is the energy. That is the energy, and because of the negative charge on the electron, and a potential well is formed. Actually, due to this particular confinement of motion of electrons in one direction, we can consider this device to be acted as a two-dimensional electron device or two-dimensional electron gas device or electron motion device, and in which the movement of electrons has the or which actually causes to produce a potential well in the intersurface layers of the two heterojunctions formed to different materials which forms a heterojunction, and that actually makes the device operational for or operational as a two-dimensional electron device. Okay, so we will see this particular device now. MOSFET structures. The main contribution to present technology in general and microelectronics in particular is probably the metal oxide semiconductor field effect transistor. This device is the basic unit of present ultra-large scale integration microelectronics industry. It is estimated that MOSFET-based electronic devices now constitute about 90% of the electronic device market. The Mosfet is formed by a MOS structure and two lightly doped P and N highly N-type junctions in which N material is heavily doped, which acts as the source and drain on the FET. Okay, so this particular device has a MOS structure which consists of two lightly doped P materials and two heavily doped N-type material junctions in which the N material is heavily doped and P-type material is lightly doped. The gate structure, the gate of the transistor is formed by the MOS structure. The semiconductor is usually P-type silicon over which a thin oxide layer, that is gate oxide that we have already seen for MOSFET structures. The gate oxide layer is actually silicon dioxide, gate oxide material. That is actually grown by thermal oxidation. The MOSFET, that is that MOSFET transistor is a semiconductor device which is widely used for switching and amplifying electronic signal in the electronic devices. MOSFET is a core of integrated circuit and it can be designed and fabricated in a single chip because of its very small size. So this MOSFET can be fabricated on a single chip as its size is very small. The MOSFET is a four-terminal device with a source, gate, drain and body. So source is represented as S, gate as G, drain D and body B. The body of the MOSFET is frequently connected to the source terminal, so making it a three-terminal device like field effect transistor. Figure A shows the structure of a MOSFET. We will see the structure of this one. So here this is the structure. So this is a P-type substrate over which a lightly doped P-type silicon layer is here, over which we have a very heavily doped N-type source, another heavily doped N-type drain, and between the source and drain there is an oxide layer. That is the silicon oxide layer that will be in between the gate terminal, that is a metal contact terminal, and the P-type semiconductor. Okay, so actually the inversion layer is formed between this oxide and the semiconductor material. Okay, so now this is the band diagram, energy band diagram for MOSFET structure. We will discuss this one after some time. Okay, so this is the structure. We have a P-type substrate, a heavily doped P-type structure over which a lightly doped P-type silicon structure is here, and in that structure this N2 N-type materials are actually grooved on this one, and this is the one is acting as a source and there is another one is acting as a drain. Both are heavily doped N-type, and in between this drain and source, of course, there is silicon oxide which is acting as the gate oxide material and over which the metal gate is actually placed, and connections are taken for this source and drain like this. Okay, so this is the structural details of the MOS transistor, and this is actually the energy band diagram with a positive strong bias voltage applied at the gate. Then we will discuss after some time. So this is the detailed structure of this one. P-type substrate is connected to the body. Usually this body and source will be joined together to make it as a three-terminal device. Then, so the MOS structure is obtained by growing a layer of silicon dioxide, that is SiO2, on top of a silicon substrate and depositing a layer of metal or polycrystalline silicon. Usually this polycrystalline silicon is used for the purpose of growing this particular silicon dioxide layer over the silicon substrate. Okay, so usually The polycrystalline silicon is used as silicon substrate, and its structure is equal to a planar capacitor. Why is it called a planar capacitor? Because what is a capacitor? Capacitor is actually two metal plates separated by a insulation layer, isn't it? So in the case of a Mosfet, actually we have silicon polycrystalline material on one side, that is the semiconductor material on one side, and another metal that is silicon oxide, over which the metallic contact of the gate is there. So the semiconductor with metallic contact is there, then silicon dioxide, that is gate oxide material with metallic contact is there. In between this one, we are actually applying the voltage, isn't it? That is a gate voltage. So it will be acting as a capacitor. So the N-type MOSFET consists of a source and a drain substrate, two highly conducting N-type semiconductor regions which are isolated from P-type. A metal or polysilicon gate covers the region between source and drain, but it is separated from the semiconductor by the gate oxide material SiO2 that we have seen already. The source and drain regions are identical in nature. It is the applied voltages which determine which N-type region provides the electron and becomes the source, while the other N-type region collects the electron and becomes the drain. So both N-type, heavily doped N-type regions are identical in nature, and which is the source and which is the drain, which determines depending upon the voltages which we apply for operating the device. The MOSFET works by electronically varying the width of a channel along with which charge carriers flow. Actually, the MOSFET, the working of the electron flow is actually controlled by the gate voltage applied, and in between the oxide layer and the two N positive means heavily doped N-type source and drain, an inversion layer. An inversion layer is formed through which the charge carriers are flown, and the charge carriers can be controlled with the help of the gate voltage. Okay, the charge carriers may be either electrons or hole depending upon the type of metal which we use, N-type or P-type. So the charge carriers enter the channel at the source and exit via the drain. The width of the channel is controlled by the voltage at the gate, which is located between source and drain. It is insulated from the channel near an extremely thin layer of metal oxide. So all these constructional features are almost very similar to the MOSFET features which you have already learned. Now we will see the working of this MOSFET, and our aim is to describe the band diagram, how the band diagram is or how the energy band is produced, or how the two-dimensional electron gas motion or electron wave motion is achieved in the at the surfaces, at the contact surface of the two materials, which actually forms this particular or which actually causes to make the device as a two-dimensional electron gas device. Okay, so now let us consider the case of NMOS. NMOS, that is negative MOS, NMOS type material, NMOS type device. So we can have NMOS or PMOS, N-type MOS or P-type MOS. First, while applying the positive VGS, actually we have to apply a gate source voltage, isn't it? That is VGS. It causes a field that starts to repel the majority carriers at the structure. So when you are applying, so this is the gate, the gate that between this P-type and the gate there is gate oxide material, which is actually shown here as yellow color, isn't it? Gate oxide material, and this is the gate and this is the drain. No, this is the gate and this is the drain. This is the drain and this is the source. So between the source and the gate we apply VGS. Between the drain and the source we apply VDS. So VDS is a positive voltage and VGS is also a positive voltage. Okay. So this VB, that backside of back contact and the gate not gate, the source, the back, that is the body of this particular uh, device, and the source is usually connected to each other so as to make the same potential. Okay, so as to make it at the same potential. So the same thing is given here separately to know the gate, drain, and source and the corresponding voltage supply. Okay, and this is the symbolic representation of the MOSFET structure. Okay, symbolic representation. When a positive potential is applied to the gate, the electrons coming from the highly doped N region and some from the bulk P silicon are accumulated at the SiO2 interface. So what is SiO2 interface? What is the SiO2 interface? This is the SiO2 interface, that is gate oxide interface. So when uh, gate, this gate source voltage, which is positive here, applied here. So what happens here? This is P-type substrate, and here this is gate oxide material, and this is the gate, this metallic compound. So what happens here? Usually this N source is here. This is the field of the source terminal is here, so source is here. So from this one, the electrons are actually attracted towards this one, and here between this P substrate and this gate, of course, the charge carriers are depleted here, this region. That are all depleted in this region because it is actually, as far as the gate is concerned, it is positive, and this is actually uh, a p-type substrate, isn't it? This is a p-type substrate. So actually, what happens when you are applying a, 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 a positive voltage here? Usually, there will be a depletion formed here, a depletion layer formed here. Okay. So on increasing VGS, the field starts to attract the minority carriers from the substrate. Actually, the substrate, though p-type material, there are majority carriers are called, but there are minority carriers of electrons that will be attracted towards the gate and form the channel. Actually, that actually causes to have a gate current. At the same time, a channel is formed due to the electrons coming from the N positive region and from some of the electrons which comes from the bulk P silicon. Okay, due to the application of the potential positive potential at the gate and source. Okay, so that actually causes to make a channel, and that channel is then this particular channel is called an inversion channel, or that is due to the inversion, or that is what is called the inversion. The uh, field produced by the gate source voltage that attracts the minority carriers from the substrate, that is p-type substrate, and form the channel, and this is what is called the inversion. The electrons from the form the inversion layer or channel. Actually, the electrons which accumulated at that region from the N positive source and some of the minority carriers in the p-types actually causes to form the inversion layer or inversion layer, which contains the charge carriers and which forms the channel. That is what is called the inversion channel. Now, if a voltage is applied between the drain and source, now a positive, suppose you are applying a positive voltage. You are applying a positive voltage between drain and source. What happens? The current flows freely between the source and drain, and the gate voltage controls the electrons in the channel. Hope you follow my point. So when we apply a positive voltage, between the source and drain, what happens here? Some of the electrons available here, or which electrons are accumulated on the inversion layer, will be uh, causing it to passes through this one, and which actually constitute a source drain to source current, isn't it? That is a source drain current, source to drain current, and that current is actually controlled by the gate source voltage, the source voltage between the gate and source, because the electrons which are available here depends upon the voltage which is applied, or that is actually the electric field produced by the gate source voltage applied. Okay, so If a voltage is applied between the drain and source, the current flows freely between the source and drain, and the gate voltage controls the electrons in the channel. And it is due to this fact, this type of transistor is called a field effect transistor, because the current which is flowing through the source to drain is actually depending upon the voltage applied between the source and the gate, or gate source voltage can control the drain source current, or which can control the voltage across the gate source can control the flow of source to drain. Okay, so that's why this particular field which controls the electron charge carriers in the inversion channel. So that's why this type of device is called a voltage controlled device. Okay, gate voltage controls the electrons in the channel. Okay. Now this is also the same thing what we have seen earlier. So N positive here, this is the drain, this is the source, the inversion channel is formed here, this is the inverse channel, and this is the gate oxide material. Okay, all these things that we have already discussed now. Now, this is the most important thing, energy band diagram of Mosfet. How can we call this device as a two-dimensional electron or 2DEG device, or two-dimensional electron gas device, or the motions through this particular device is a two-dimensional electron gas motion. That is explained now, that we can discuss here now. Consider the schematic energy band diagram of the MOS structure for four different values of Vg, and we consider four different values of Vg, that is gate voltage, and the gate potential which is applied on the gate of the device with respect to the substrate. Okay. Now, first case is when the gate voltage is 0. That is a flat band case. So we will see the band diagram here. See the band diagram here. This is actually the energy band diagram for the device. So this is the silicon oxide layer, and then this is the metal contact over which we are giving the connection, and of course this is the semiconductor region. So here you can see the metal and the semiconductor region, the Fermi level are almost coinciding with each other. That is because this is a neutral case, isn't it? Because no gate voltage is applied, right? This is the case when now gate voltage is, that is Vg is equal to 0. Applied gate voltage is 0. This is the energy band diagram for this one. So the Fermi level for both case, that is the metal contact region and semiconductor region almost superimposes, or which actually coincide with each other. Okay. Now we will see the second case, that is Vg, that is gate voltage is less than 0, that is negative. When you apply gate voltage which is negative in nature, what happens? That we will see now. Okay. For a negative gate voltage, that is Vg less than 0, an electric field is set up in the oxide layer, isn't it? So even if the gate voltage is negative, an electric field is set up. The negative gate voltage causes the silicon bands to bend up at the oxide interface. Actually, here you can see this is the silicon that here this energy band actually bend upside. That is like this. So this is that is what's called bend up. The energy band is actually bend upside when the gate voltage is negative. That's so gate voltage is negative means less than 0. So the energy band at the interface of the silicon oxide and the semiconductor is bent up like this. Okay, this is the nature of the band structure in the case of a gate voltage which is less than negative. So what is the reason for that? We will see. Don't worry. Okay. So that the Fermi level, that is when the silicon band bands to bend up and at the oxide interface, so that the Fermi level is closer to the valence band edge. So when the silicon bands, that is the semiconductor energy bands bend up, what happens? The Fermi level is closer to the band, it's a valence band edge, isn't it? This is the Fermi level. The Fermi level is closer to, this is the valence band, and this is the, above this one is the conduction band, isn't it? For this one. So here actually, this Fermi level is closer to the valence band. Fermi level is closer to the valence band for this particular condition. Okay. Thus, extra holes accumulate at the semiconductor oxide interface and electrons accumulate at the metal oxide interface. So actually, under this condition, that is when the gate voltage is negative, the silicon bands bend up at the oxide interface. Oxide interface in the അടുത്തേക്ക് അത് മുകളിലേക്ക് ബെൻഡ് ചെയ്തുകൊണ്ടാണ് ബാൻഡ് സ്ട്രക്ചർ ഉള്ളത്. മാത്രമല്ല, the Fermi level is closer to the valence band, and moreover, extra holes accumulate at the semiconductor oxide interface. Semiconductor oxide interface extra holes are accumulated and the electrons accumulate at the metal oxide interface. So at the metal oxide interface, this is the metal. So at the metal oxide interface, actually what happens at the metal oxide interface, electrons accumulate, and also at the that semiconductor interface. Semiconductor interface where the holes are accumulated. Okay. So let us consider the case 3, that is the gate voltage is less than the threshold voltage. So threshold voltage, we will see what is the threshold voltage. So threshold voltage Vt is greater than Vg, or Vg is less than the Vt, but Vg is greater than 0. So gate voltage is greater than 0, that is gate voltage is positive, but at the same time the device is not starting operation because the threshold voltage for the operational device is more than that of the gate voltage. If that is the case, what is the condition or what happens to the device? That we are going to see now. The voltage Vt is defined as the gate voltage where the intrinsic Fermi level and actual Fermi level are coincident at the interface. That is the voltage Vt. What is voltage? That is the threshold voltage. The threshold voltage for the device, that is Mosfet device, is defined as the gate voltage where the intrinsic Fermi level and actual Fermi level are coincident at the interface. See this one. See here that this is the this is actually the intrinsic Fermi level and the actual Fermi level we have already seen. Both are actually coinciding with each other, isn't it? So here this intrinsic Fermi level and actual Fermi level of the device, which are coinciding with each other when the gate voltage is greater than 0, that is positive at the same time, which is less than the threshold voltage. When the device has not started operating, it is just on starting operation. If the Vg is greater than Vt, the device start operates. Okay, so what is that condition? We will see. See, the voltage Vt we have seen. What is the voltage Vt? Vt is the gate voltage where the intrinsic Fermi level and actual Fermi level are coincident at the interface. Interface means interface of the silicon oxide and the semiconductor. That is gate oxide material and the semiconductor. Okay. The size of the size of this depletion region. The size of this depletion region increases as Vg increases. As Vg crosses Vt, that is, if Vg is greater than Vt, what happens? The depletion region, which has been created at the drain side, that is in the inversion channel layer, at the drain side, the depletion region increases as Vg increases. For the depletion region, the silicon bands bend down at the interface, resulting in a depletion of holes and a negatively charged layer of localized state is formed at the semiconductor oxide interface. So that is the peculiarity here. So here, see, here when the voltage Vg is greater than the threshold voltage, so that actually causes to make this band structure bending down like this. So this is the actual operation condition of the device. So here, this is the metal oxide, and this is silicon oxide, that is oxide layer, and this is the semiconductor layer, isn't it? So here the band structure bend downs. So here it actually, when Vg is less than 0, it bend ups. Here it is bending down, the band structure is bending down, and here you can see the gate voltage is greater than Vt, or under this condition, then if you connect a drain to source voltage, that will create a drain current, that will send a drain current IDS, that is drain to source current. Okay, so here what happens when this when the drain, when this particular condition is there and the device start operating, see, when Vg increases, what happens? Vg increases, what happens? The depletion region size also increases. And for the why is it so? Initially, of course, that will be due to the positive voltage applied between the drain to source. When the positive voltage is applied between the drain to source, what happens? Since the drain is actually connected to a heavily doped n-type material, and it is connected with positive, means actually between the substrate and the n-type drain, there is a reverse potential, isn't it? There is a reverse biasing. So that reverse biasing causes to make the depleted region there, where the depletion regime actually causes to make the SI band downwards. The SI band bend downwards at the interface, and resulting in depletion of holes. The depletion of holes are taking place, and localized negatively charged. So more and more negative charges are being accumulated. So that is why it is called a negatively charged layer of localized states. So more and more localized states of negatively charged uh, electrons, or negatively, that is negative, electrons are negatively charged, and that electrons are will be accumulated, or that will be accumulated and finally gone through the drain to source as the IDS, as IDS. Okay, so charged layer localized state is formed at the semiconductor oxide interface. So this negatively charged localized state, that actually causes to have a electron motion, a 2D electron gas motion through the inversion layer. So that is actually the charge transition, or charge transfers through the inversion layer, and through the drain to source as the IDS, or drain to source current. Okay, or drain current. Okay. Now the charge diagram also you can see here. When Vg is less than 0, the charges are actually here. This is on this side. Here actually this band diagram, which is bend upwards, where charges are charge positive here, positive 2, and this negative 2. Here also actually Vg is less than 0, but it is not at the threshold. The device is not started working. So here actually charges are accumulated on the that metal oxide side, but here it is less. That is why, though the bands, silicon bands are actually bend downwards, but the device is not start operating. But when Vg is greater than its threshold value of the voltage, Vg is greater than the threshold value of voltage, the device starts operating. Of course, here the charges, actually what happens, more and more number of depletion of the holes takes place here, and electrons are localized. The electrons are on the inversion channels there due to this one, and that actually causes to have the electron gas formation, and that causes to make the device operational, and so, and thus the the electron motion through the inversion layer is taking place. Okay, so this is actually the for different conditions of the working of the Mosfet with the help of a energy band diagram. So this you have to by heart. If you are asked to explain the operation of the Mosfet, then you have to draw this one with all these diagrams, the applied voltage condition, the energy band diagram in each case, and also the charge diagram. Charge diagram means how the charge occurs and what are all the charges which developed on either side of the interface of the material, silicon and the oxide material. Okay. Now, so this is also how this depletion rate is grown when VD is applied. So what actually causes to grow the depletion region, how the depletion region is thickened, that is shown here. Okay. So that I have given very detailed explanation of this one. I have given in the note. You can refer the note also. So the corresponding positively charged regions at the metal oxide surface is also shown. But for Vg greater than Vt, that is when the device is getting operated, that is the gate voltage is more than the threshold voltage Vt, the intrinsic Fermi level at the interface drops below the actual Fermi level. That is the important thing you have to note down again. Here you can see. So here you can see the intrinsic Fermi level has just dropped down. When the condition is here, the intrinsic Fermi level has now dropped down. Now the new Fermi level is this one. So when this one has when the device, the silicon band has been bent down. So here the Fermi level, the intrinsic Fermi level and the new Fermi level, that is due to this bending down when the device is operated. Of course, this is the new Fermi level that has shown here, and that is the actual Fermi level is just lower than the new Fermi level which is formed here. Okay, that is what has been given, that has been explained here now. The actual Fermi level forming the intrinsic Fermi level at the interface drops below the actual Fermi level, forming the inversion layer. Actually, when Vg is greater than Vt, this inversion layer is formed and localized electron states are observed in the operation of the device. Okay, so it is on this particular inversion layer the mobility of electrons are taking place, or the mobility of electrons or mobile electrons reside in this inversion layer. Depending upon the gate voltage applied, these electrons are actually having high mobility through the inversion layer, and that is then flown as a drain current through the drain to source current through the drain terminal, isn't it? The electrons coming from the N positive region, that is heavily doped N region, and some from the bulk P region are accumulated at the SiO2 interface. SiO2 means silicon and silicon oxide. Silicon oxide is the gate oxide material, silicon is the substrate material. And at the interface of these two materials, that is when these particular materials are joined together at the interface, what happens? The electrons and electrons coming from the heavily doped N region, that is from the source, and some of the electrons from the bulk P region that will be accumulated on the inversion layer that will be accumulated on the interface between the silicon oxide and the silicon substrate. Okay, the electrons in this inversion layer can be confined so as to exhibit a two-dimensional behavior. So this property of the device is actually made it as a two-dimensional electron gas device. The electrons in the inversion layer, the electrons which are residing in the inversion layer can be confined. That can be confined into a two-dimensional electron motion. That is why we can quantize this particular electron motion. Okay, so this inversion layer electrons can be confined so that this particular device will show, or the particular device will exhibit a two-dimensional behavior. So when it exhibits a two-dimensional behavior means the electrons can move on two-dimensional basis, so that one of the dimensions the electron motion is confined. So they can be controlled by the gate voltage in the MOSFET. So this two-dimensional behavior or two-dimensional motion of the electron can be made possible by controlling the gate voltage. So that is why this particular device is called a two-dimensional electron test device for two-dimensional device, which will exhibit the two-dimensional behavior. If a positive potential is applied between drain and source, the electrons, the channel will create a current. That is the drain current. I told you already. The current can be modulated by changes at the potential at the gate, since the amount of electrons in the inversion layer depends on the magnitude of the electric field produced by the gate source voltage or across the insulator. Insulator means the silicon oxide, between the silicon oxide and the silicon substrate. Okay, there the inversion layer is there. Okay. Now let us consider the VI characteristics of MOSFET. The VI, what is meant by volt ampere characteristic of the device? For any device like this, for a transistor, the volt ampere characteristics, the voltage that is the drain current, drain to source current is the plot between the drain to source current when a drain to source voltage is applied for a particular gate voltage. Or VI characteristic of MOSFET is the relation between the drain current ID and the drain to source voltage VDS or VD for a constant gate voltage VG. For VD is equal to 0, there is obviously no current and between the source and the drain, since both are at the same potential. And when VD is greater than 0, the inversion layer or channel acts like a resistor. So actually this inversion layer acts like a resistor, but still then depending upon the type of voltage value VD, so what that is the magnitude of the voltage, how much VD is applied. Depending upon that VD, the inversion layer will be acting as a resistor, so that will be allowed to flow through a drain current ID. Though it will be acting as a resistor, but it will be allowing a drain current ID. Right? Increasing VD imposes a reverse bias on the heavily doped P drain region. Heavily doped N-type drain and a P-type separate region, because drain to source is actually a reverse voltage. That is a positive voltage applied at the N-type, heavily doped N-type drain. So that will always make a reverse biasing, isn't it? Reverse biasing between the drain and the P-type substrate. That is what is given here. Thereby increasing the width of the depletion region and decreasing the number of carriers and narrowing the channel in the inversion layer. So even if we are going on increasing VD, then what happens? The depletion region width will be increased, and that actually causes to decrease the carriers, and which narrows the channel in the inversion layer, and that actually narrows the narrows the channel or inversion layer, so that the number of charge carriers will be less. If VD will be further increased, what happens? So there is a condition what is called the pinch-off condition. So pinch-off condition takes place. And this pinch-off condition is actually taking place at a particular voltage, what is called the VD sat. That is the saturation voltage of the saturation voltage, that is VD sat. That is the saturation voltage of the drain voltage, saturation voltage of the drain voltage, that is VD sat. That is the current which is flows at that particular condition is called ID sat. Okay. Further increase of VD, the drain voltage, drain to source voltage, if you are going on increasing more than VD set, what happens? ID will not be increasing. There is no increase in ID. Even if VD increases, ID will not be increasing. That does not increase ID, and rather it causes a saturation of the device. So device will be getting saturated. Saturation is caused by a decrease in the carrier density in the channel due to pinch-off phenomenon. Actually, once the device is getting saturated, what happens? The carrier density in the channel, in the inverse channel or the inversion layer, will be very less, and also that is mainly this carrier density is decreased, and that is mainly due to the pinch-off phenomena. So this is the ID versus VDS, and this is ID. So this is the y-axis. We take the ID in ampere and the VDS in x-axis. So you'll be getting different curves like this for a gradually increasing Vg. For this is for one Vg, and this is for another Vg, and this is for another Vg. For each case, Vg is made constant, and then increasing VDS, and you will be getting different ID. So you can plot this graph, and that will be giving uh, the VA characteristic of the Mosfet. Okay. ID versus VD curve are plotted for fixed values of Vg greater than Vd as shown in the figure. I have just shown you. Vd sat increases with increasing Vg. So the Vd sat, the saturation voltage of the drain to source voltage will be increased. That value will be magnitude can be increased by increasing the value of Vg. Actually, Vg controls the charge carriers available on the inversion layer. So actually, this is the electric field produced by the gate source voltage VGS that actually causes to have the number of charge carriers available on the inversion. That is why this particular device is essentially called a voltage controlled device. Okay, because the control of electron carriers or electron charge carriers in the inversion layer is depending on the gate source voltage. The advantages of Mosfet devices lie in the speed of their operation and in the ease with which they can be fabricated into ultra small devices. The main advantage of this particular device is that it's a very fast device. It's a fast operating device. The speed of operation of this device is very fast, and also this device can be fabricated in an ultra small device. It can be fabricated in an ultra small device, such a small size. In order to exhibit the quantum effects at the silicon oxide interface, the following conditions are required. What are those following conditions? What are those conditions? The SiO2 insulator of amorphous nature should have neither high concentration of impurities. So the insulator means gate oxide material, that is the silicon oxide. The gate oxide insulator material should have neither high concentration impurities, that is, should not have high impurities concentrations, nor there should not be any trapped charge. It should be free of trapped charge. There should not be any trapped charges available on this silicon oxide material, which is used as the gate oxide material. Then the second thing is that the smoothness of the Si-SiO2 interface, that is the interface between the silicon wave substrate material and silicon gate oxide material, that interface should be the smoothness of the Si-SiO2 interface should be controlled at atomic size level. So that interface material should be, and that particular interface smoothness of the material should be controlled at atomic level size. Since a rough surface on top of the inversion channel would greatly decrease the electron mobility in the inversion layer. So if the interface between the Si-SiO2 layer is rough, if it is a rough surface, then the inversion layer formed at that interface will have the electron mobility lesser. So the inversion layer formed between the interface will be having electrons which have mobility which is less. Okay, so that is why these two conditions must be satisfied in order to exhibit the quantum effects for Si-SiO2 interface. So what are those one? The first one is this particular material, SiO2 material, that is essentially an insulator gate oxide material that is of amorphous in nature, that should have neither high concentration of impurities and it should have no trapped charge. Okay, what is the second condition? The smoothness of the interface should be controlled at atomic size level. Such a very fine leveling must be there. Atomic size leveling must be there. Because the rough surface on top of the inversion channel will greatly influence the mobility of the electrons. Or if it is a roughened surface, the mobility of electrons will be less. In the Mohs structure, although the electrons are confined along the perpendicular direction, they are practically free to move in the plane of the interface. Okay, so this is as far as the working of this particular device is concerned. Then again, the shape of the quantum well is due to the space charge of the ionized acceptors in the p-type silicon, whose corresponding faults are repelled by the electric field across the dielectric oxide produced by the positive gate potential. The shape of the quantum well formed is actually a triangular quantum well only. And this triangular quantum well is due to the space charge of the ionized acceptors in the p-type silicon and whose corresponding faults are repelled by the electric field produced by what? Produced by the gate source voltage VGS. Okay, that is the positive gate potential. If a positive potential is applied between drain and source, the electrons in the channel will create a current. That I had told you. The current can be modulated by changes at the gate potential, since the amount of electrons in the inversion layer depends on the magnitude of the electric field produced across the insulator and the silicon. Insulator means silicon oxide insulator, gate oxide material and the silicon wafer. Okay. The name field effect transistor is the control effect of the electric field at the gate source voltage applied to the gate. That is why this particular transistor is called a field effect transistor, because the control of charge carriers in the inversion layer is essentially controlled by the electric field produced by the gate source voltage applied. Okay. Now, the electron inversion layer of the Mosfet can be considered as a two-dimensional system of electrons immersed in a triangular shaped quantum well. Here the quantum well formed because this is a two-dimensional system we have seen now, and the two-dimensional system here the quantum well formed is a triangular quantum well. That is the shape of the quantum well. It's almost like a triangular quantum well. That's it's called a triangular quantum. In the quantized values of energy confinement in triangular quantum well can be which can be explained as E is equal to, that is energy confinement, E is equal to En plus h cut square kx square, that is k vector, kx square, because it is two-dimensional confinement. That is why we have k and kx and ky. So that is the k vector on h cut square 2m star x, kx square plus h square, h cut square 2m star y, k square y, where En corresponds to the quantized energy of the triangular well. And this is actually the energy confinement or the energy of a triangular quantum well that you have to by heart, right? That this particular energy equation you have to by heart. Okay. You have to by heart this energy equation. E is equal to En plus h cut square by 2mx kx square and h cut square by 2my m star y. That is the m star y means m star is actually the effective mass of the electrons in the y direction, effective mass of electrons in x direction, and kx square, that is the k vector square in the x direction. K, that is actually the three-dimensional plane wave motion is confined in the two-dimensional k vector, isn't it? Two-dimensional motion of or two-dimensional k vector motion, or that is two-dimensional electron gas motion on k vector, isn't it? Where En corresponds to the quantized energy for the triangular wave, and this is again equal to En is equal to 3 by 2 pi into n minus 1 by 4 raised to 2 by 3 e square f square h cut square divided by 2 m star z, where n is equal to 1 2, and this is the energy En actually this is energy En for a two-dimensional quantum well, and the energy value En is given here, and that with this particular that is this particular expression that will give the total energy. This is the total energy for the quantum confinement of a triangular shaped quantum well, and here this En is given by this particular, En is approximately given by this particular equation. The density of state dose function corresponds to two-dimensional cases given by the G is equal to GV m star T divided by h cut square, where GV is the conduction band degeneracy that we have already seen what is meant by conduction band, degeneracy, and all those things we have seen. And this is the energy subbands. So the energy subbands which is shown here, and the lower value of this particular, this one actually represents what, that is the value of En. The bottommost this energy level actually representing the value of En here, and this for each that level, energy level, n is equal to 1, n is equal to 2, n is equal to 3, like that levels of energy. So this is the energy subband structure, subband diagram. And what is meant by conduction band degeneracy? The conduction band degeneracy arises from the fact that constant energy surfaces of the silicon conduction band are formed by 6 ellipsoids in the direction 0, 0, 1 momentum space. So actually, the conduction band degeneracy can be explained in momentum space. Momentum space means actually we have for this particular device, we have the conduction band degeneracy, which can be explained in momentum space. And in momentum space, this is the 0, 0, 1 direction, and this is 0, 0, 1, 0 direction, and this is 1, 0, 0 direction, like that. So these directions are actually mentioned like this. So for each one of, for 0, 0, 1 direction, actually the conduction band region, actually this is arising from the fact that constant energy surface of the silicon conduction band are formed by 6 ellipsoids in the 0, 0, 1 direction. So this is 0, 0, 1 direction. So the electron wave motions actually, this is actually this, to this direction the electron motions are confined. So the conduction band degeneracy, which can be explained on this with the help of these 6 ellipsoids in the direction of 0, 0, 1 momentum space. Okay, that is 0, 0, 1 direction of the momentum space. So this is the momentum space in which we have the different directions shown here. This is 0. In the y direction it is 0, 1, 0. That's the z direction it is that is x direction it is in 1, 0, 0, and 0, 0, 1 direction is the kz direction. The long axis of the ellipsoid corresponds to the longitudinal and effective mass. That is, the effective mass of the electrons on the long axis is actually m, representing as m star I. That is 0.91 m0, where m0 is the mass of the electron. Okay, and the two equal short axes to the transversal effective mass m star t. That is, for a long star, if this is the long axis, then this is the short axis. This is the short axis. Okay, this is the short axis. But in the short axis, the effective mass of electrons will be 0.19 m0, and for long axis is 0.91 m0, where m0 is the mass of the electron. Okay, so this is the ellipsoid representation for the momentum space in which the constant energy surface in silicon around the minima of the conduction band is shown. So ഇത് മനസ്സിലാക്കിയാൽ മാത്രം മതി. This is not a very simple thing. The only thing is that the electron motion at the surface, of course, the conduction band degeneracy arises, and that actually causes to have a constant energy surface of the silicon conduction band, which are actually formed by 6 ellipsoids in the direction 0, 0, 1. That is this one, the z axis. That is kz vector axis in the direction of momentum space, through which we can explain this particular conduction band degeneracy and the mass of electrons. And this is the conduction band series. So this is actually the series. This is for E0, and the Fermi level is also shown, and this is for again E1, that is the conduction band degeneracy. See, here again the band is like this, and here there are 3 bands like this, like this. So this is for E0, this is for E1, this is for E2, and like that it goes. Okay. So distance from nanometers versus electron energy in units. So energy band series conduction band profile. This is the conduction band profile. Just like what we have seen the degeneracy case. The degeneracy we have seen, conduction band degeneracy we have seen, the constant energy surface for the silicon conduction band. So when we consider about the conduction band, the conduction band subbands, how the subbands which are actually what are all the profile of the conduction subbands, energy subbands, conduction band energy subbands, that is shown here. You just understand this one, okay? So this is not that much important, but you have to know that is how this conduction band that degeneracy is there, and what is the direction of the conduction band electrons which actually um, moves, or which actually have the motion. This you should know. The diagram shows the result obtained for the energies for the case of a silicon Mosfet with the insulating oxide grown over a 001 silicon surface. So actually, this is actually the silicon Mosfet with the insulating oxide, that gate oxide insulation, which grown over the direction of 001. The results are obtained by the self-consistent numerical solution of problem. Actually, this is a case condition in which the Mosfet is fabricated with gate oxide metal as silicon, and which this silicon oxide is grown over 001 silicon surface. Okay. The subband of energy E0, E1, E2 corresponds to M star L and E0, E1, E2 dash to M star T. That is shown here. Subband series, what I have told you. This is the energy subband series. So you just understand that's all. These are all the energy subbands which are actually exhibiting by the device. Energy subbands which are actually the energy subbands, conduction band energy subbands. Okay. The solid curve represents the conduction band profile. We said the squared wave functions over the two subband series are also represented. Squared wave function for the two subband series that I have told you. So the squared subbands actually shown by the dotted curve here. Squared subbands. So just understand that. Okay. So with this, I conclude the session on Mosfet. So Mosfet is actually the Mosfet construction features you might have already learned in your previous semester classes. But how this device can be considered to be a two-dimensional electron gas device, or a two-dimensional system, and how this device behave as a two-dimensional electron gas system, and what are all the band structure then, and how the device behave, and all those things we have explained now. And just read my notes and carefully, that will give you more understanding about this particular subject. Okay, thank you very much for patiently listening my lecture session.